October 14th, 2024, 12:06 p.m. Eastern, Kennedy Space Center. The ground shook as a Falcon Heavy lifted the largest spacecraft ever sent to another world into the Florida sky. Not to Mars, the planet we've obsessed over for 50 years. To a moon most people have never heard of. A moon hiding an ocean twice the volume of every ocean on Earth combined. And 4 days ago, November 7th, 2025, scientists discovered something about another ocean world that changes everything we thought we knew. We were looking at the wrong worlds this whole time. For half a century, humanity searched for one thing in our solar system: water. Not just ice locked in polar caps, not just traces frozen in regolith. Liquid water. The universal solvent, the cradle of every living thing we've ever discovered. The molecule that makes life, as we understand it, possible. Mars was the target. Mars was always the target. We sent orbiters, landers, rovers, spent billions of dollars and 50 years of human ingenuity searching for evidence that Mars once had rivers, lakes, maybe even oceans. And we found hints: dried channels carved by ancient floods, minerals that only form in water, ice beneath the surface. Evidence that 3.5 billion years ago, Mars might have been wet. But that was then. We thought we'd found water flowing on Mars today. Mysterious dark streaks appearing on canyon walls and volcanic slopes during Martian summer. They looked like seeps, like springs, like water finding its way to the surface. Scientists called them recurring slope lineae. The media called them proof of liquid water on Mars. We wrote papers, made announcements, got excited. They're wind patterns, just wind sculpting dust. And on March 1st, 2025, a spacecraft the size of an SUV with solar panels spanning a basketball court screamed past Mars at 39,000 miles per hour. Not to study it, to use its gravity like a slingshot, accelerating towards something far more promising. Something we'd overlooked for decades while we stared at Mars's empty riverbeds. Jupiter and its moons. While we obsessed over a dead planet's ghost stories, Jupiter's moons were hiding oceans. Entire oceans, with everything life needs. We just didn't know where to look. Before we go further, you need to understand why this matters. Why water is the only molecule scientists truly care about when searching for life. Water isn't special because it's abundant. Half the universe is hydrogen. Oxygen is common too. Water is special because it's weird. Most liquids contract when they freeze. Water expands. Ice floats. Think about that. This one quirk, this strange property where frozen water is less dense than liquid water, kept Earth's oceans from freezing solid from the bottom up during ice ages. It created insulated pockets beneath ice where life could persist through global freezing events. Without this property, complex life on Earth might never have survived long enough to evolve. Water dissolves more substances than any other liquid in the universe. It's why your blood can carry nutrients and oxygen, why cells can perform chemistry, why oceans become laboratories where simple molecules meet, bond, and occasionally spark into something more. Carbon-based life, the only kind we know, receiver a solvent, a medium where chemistry can happen. Water is the best we've ever found. Where there's liquid water, there's possibility. Where there's liquid water with organic molecules and energy sources, there might be life. For 50 years, we thought that meant Mars. Past tense Mars. Ancient Mars. A world that lost its water billions of years ago. We were searching a graveyard. Meanwhile, the outer solar system was hiding something extraordinary. Europa Clipper will arrive at Jupiter in April 2030, 5 years from now, after traveling 1.8 billion miles through the solar system. By then, it will have endured extreme radiation that would fry most electronics in seconds. It's shielded inside a vault of titanium and aluminum, thick enough to protect its instruments from Jupiter's belts of charged particles. A radiation environment more hostile than standing next to a nuclear reactor. It will conduct 49 flybys of Europa over 4 years, diving through that radiation repeatedly, each pass bringing it as close as 16 miles from the surface, closer than a transatlantic flight is to Earth. But we've known Europa's secret for almost 30 years. December 19, 1996. NASA's Galileo spacecraft, already crippled by a failed main antenna that reduced its data transmission to a trickle, swept past Europa at just 430 miles above the surface. It was the mission's 4th close pass of the mysterious moon. The magnetometer went haywire. Galileo's magnetometer measured magnetic fields using sensors mounted on an 11-meter boom extending from the spacecraft. That boom had to be rigid. Any bending or twisting would contaminate the data. They calibrated obsessively. And as Galileo passed Europa, the magnetometer detected something impossible. The moon's magnetic field was backwards, fluctuating, as if something conductive was sloshing around beneath the ice, generating its own field that opposed Jupiter's. Dr. Margaret Kivelson, UCLA planetary scientist and the magnetometer's principal investigator, described it as a substantial magnetic signature, pointing in an odd direction. Europa's north magnetic pole was oriented strangely, about 1/4 the strength of Ganymede's field, but definitely there. The only explanation: a global ocean of salt water, electrically conductive, moving beneath the ice as Europa orbited Jupiter. An ocean. Beneath 10 to 15 miles of ice lies a global ocean. Not a lake, not a sea. An ocean that engulfs the entire moon. Salty, liquid, containing twice as much water as all of Earth's oceans combined. Let that number sink in for a moment. Europa is smaller than our moon. A frozen ball just 1,940 miles across. You could drive around it in less time than it takes to cross the United States. And it holds more liquid water than our entire planet's surface. But here's what makes Europa genuinely shocking. It shouldn't be liquid. At 5 times Earth's distance from the Sun, temperatures average -260 degrees Fahrenheit. Europa's surface is cold enough to freeze carbon dioxide solid. By all rights, this moon should be an ice ball through and through. Instead, it has an ocean. A warm ocean. Jupiter's gravity is brutal. As Europa orbits, Jupiter's gravitational field stretches and compresses the moon like a stress ball. The crust flexes. The interior heats from friction. That tidal heating, gravity turned into warmth, keeps the ocean liquid. The ice cracks under the stress, shifts, creates pressure ridges and chaotic terrain that makes Europa's surface look like Arctic sea ice photographed from above. And sometimes, maybe, it erupts. In 2018, scientists reanalyzed old Galileo data from a 1997 flyby. The same instruments, the same pass, but with new computational models. They were looking for something specific. Magnetic field signatures that would match water vapor plumes. They found one. A brief, localized bend in Europa's magnetic field at exactly 200 kilometers altitude. The kind of signature you'd expect if Galileo had flown through a plume of ionized water vapor. Just like the plumes scientists had recently discovered on Saturn's moon Enceladus. Galileo might have flown through a geyser erupting from Europa's ocean, without anyone realizing it for 20 years. Europa Clipper carries an ultraviolet spectrograph designed specifically to hunt for these plumes. If Europa is venting ocean water into space, if the ice cracks open and pressure forces liquid out like champagne from a shaken bottle, Clipper will find it. And if it does, we can sample Europa's ocean without ever drilling, without ever landing. We can fly through it and taste what's down there. We already have hints of what that might be. Scientists have found evidence of organic molecules on Europa. Carbon-based compounds detected in surface ice, possibly from the ocean below. The building blocks of amino acids, the precursors to proteins. The chemistry that, on Earth, became life. Europa has water, it has organics. It has energy from tidal heating. It has time. Billions of years for chemistry to experiment in the dark. It has everything life needs. But Europa isn't alone. February 17, 2005. NASA's Cassini spacecraft, having arrived in orbit around Saturn 6 months earlier, received new instructions. Fly closer to Enceladus. Much closer. Enceladus wasn't a priority target. It was small, just 310 miles across, about the width of Arizona. Bright white, featureless in images from Voyager spacecraft that had passed through the Saturn system in 1980 and 1981. Nobody expected anything interesting. Cassini flew past at 730 miles altitude, close enough for its cameras to resolve surface features. What they saw stopped the mission team cold. The southern hemisphere was young. Impossibly young. 4 massive fractures cut across the south polar region like claw marks. Scientists would come to call them tiger stripes. Damascus sulcus, Baghdad sulcus, Cairo sulcus, and Alexandria sulcus. Each fracture was 130 kilometers long, 2 kilometers wide, 500 meters deep, flanked by ridges 100 meters tall. And they glowed. Cassini's composite infrared spectrometer measured temperatures. The tiger stripes were 180 degrees warmer than they should be. At the moon's south pole, the region receiving the least sunlight, these fractures were radiating heat. Something beneath the ice was warm. Something was active. July 14, 2005. Cassini's next flyby brought it within 170 kilometers of the surface, closer than the International Space Station orbits Earth. The ultraviolet imaging spectrograph was watching for any sign of an atmosphere or emissions. The magnetometer was tracking magnetic fields. The plasma detectors were searching for charged particles. And then they saw it. Water vapor, shooting into space at 800 miles per hour, 200 kilograms per second. Enough to fill an Olympic swimming pool in 4 hours. Not seeping, erupting, like geysers, like Old Faithful, in space. Dr. Carolyn Porco, leader of Cassini's imaging team, would later describe the moment. We realized we were looking at water ice fountains erupting from the interior of this little moon. Enceladus wasn't dead, It was spraying its ocean into space for everyone to see. Over the next decade, Cassini would complete 23 close flybys of Enceladus. It would fly through the plumes repeatedly, sampling them directly with instruments designed to analyze dust and gas. And with each pass, the mystery deepened. The plumes weren't just water. They contained organic molecules, complex ones: carbon dioxide, methane, ammonia, acetylene, propylene, formaldehyde, hydrogen cyanide, the building blocks of prebiotic chemistry. In 2011, scientists analyzing samples from Cassini's plume flybys discovered sodium salts in the ice particles, proof that the water came from a salty ocean, not surface ice. When salt water freezes slowly, it expels salt. The fact that these grains were salt-rich meant they came from liquid, not solid ice. In 2015, Cassini detected molecular hydrogen in the plumes, evidence of hydrothermal vents on Enceladus's ocean floor, where hot water reacts with rock, producing hydrogen. On Earth, these vents host thriving ecosystems in total darkness. Then came June 2023. Scientists reanalyzing old Cassini data discovered phosphorus, specifically phosphates, in Enceladus's plumes. Phosphorus, the sixth essential element for life, the backbone of DNA, the energy currency of cells, one of the hardest elements for astrobiology to find because it's usually locked in rocks, unavailable for biology. Enceladus has it, in abundance, 100 times more phosphorus than Earth's oceans. Life requires 6 essential elements: carbon, check; hydrogen, check; nitrogen, check; oxygen, check; phosphorus, check; sulfur. We're still looking, but the chemistry suggests it's there too. Enceladus has the periodic table of life. Then came October 2025. Just weeks ago, scientists reanalyzed yet more Cassini data. Measurements from flybys conducted years before Cassini's mission ended in 2017. Using advanced computational techniques unavailable during the original mission, they discovered new organic compounds in the plumes, nitrogen and oxygen-bearing molecules that could serve as precursors to amino acids, the building blocks of proteins. And then, 4 days ago, November 7th, 2025, the announcement that changes everything. For 20 years, scientists believed Enceladus only released heat from its south pole. The tiger stripes, the geysers. Active there, dormant everywhere else. They were wrong. By comparing Cassini's infrared measurements from 2005 and 2015, winter and summer at Enceladus's North Pole, scientists discovered the North Pole is 7 degrees Celsius warmer than it should be. Heat is flowing from both poles. Enceladus's entire ocean is thermally active, heated from below, stable, balanced. This isn't a temporary hotspot. This is long-term thermal equilibrium, the kind of stable, warm environment where complex chemistry, maybe even biology, could develop and persist for millions, maybe billions of years. Enceladus is 54 gigawatts of power output across its surface, perfectly matched to the tidal heating input from Saturn. Energy in equals energy out. The system is in balance, has been for geological ages. If life exists in Enceladus's ocean, it's had time. And we know where it's going. The water Enceladus shoots into space doesn't all fall back. Some escapes, freezes into microscopic ice particles. And over millions of years, Those particles have created Saturn's E-ring, an entire ring system fed by one tiny moon's ocean. We're seeing an alien ocean vented into space, creating beauty on a planetary scale. Enceladus isn't hiding its ocean, it's advertising it. Now forget everything you just learned about water, because Saturn's largest moon, Titan, plays by different rules. January 14th, 2005. The European Space Agency's Huygens probe separated from Cassini and plunged into Titan's atmosphere. For 2.5 hours, it descended through orange haze, deploying parachutes, snapping photos, recording data. At 4,000 feet above the surface, its cameras resolved features: rivers, channels, shorelines, what looked like a dry lake bed. It landed with a soft thud, the first and so far only landing in the outer solar system. The first time humanity touched down in a place where water is stone and methane flows like water. Titan was cold, minus 290 degrees Fahrenheit, colder than any winter on Earth. But it wasn't dead, it was wet. Cassini's radar pierced Titan's haze and revealed what optical cameras couldn't see. Lakes, hundreds of them, clustered near the poles. Seas larger than North America's Great Lakes combined. Kraken Mare, Ligeia Mare, Punga Mare, bodies of liquid covering thousands of square miles. But they weren't water. Methane, ethane, liquid hydrocarbons, the stuff that would ignite instantly in Earth's oxygen-rich atmosphere. On Titan, they pool in basins, flow in rivers, evaporate into clouds. Titan has weather. Instead of water evaporating from oceans, forming clouds and falling as rain, Titan does it all with methane. Methane evaporates from lakes in Titan's summer, rises into the atmosphere, condenses at altitude into clouds made of methane and ethane droplets, drifts poleward, and falls as rain. Liquid methane rain, carving channels through icy bedrock, flowing into rivers, collecting in seas, completing a hydrological cycle eerily similar to Earth's, just 500 degrees colder and chemically inverted. Scientists studying Titan's river networks noticed something strange. Rivers flow into the seas, but there are almost no deltas, no sediment fans where rivers should deposit material. Where does it go? The leading hypothesis: Titan has a subsurface system. Underground channels, methane aquifers beneath the crust, a hidden hydrology we can't see. Beneath the surface, Titan might have liquid methane flowing through porous ice. Maybe even a water ocean deep below. Because Titan, like Europa and Enceladus, experiences tidal heating from Saturn. That warmth might sustain liquid water beneath miles of ice and organic sludge. Two layers: methane above, water below. Two potential habitats for two completely different kinds of chemistry. August 2025. NASA researchers made a breakthrough. They simulated Titan's lakes in the lab. Liquid methane at minus 290 degrees, mixed with nitrogen and organic compounds. Then they introduced molecules capable of forming membranes. The molecules self-assembled into vesicles, tiny bubbles, cell-like structures with interiors separated from exteriors. On Earth, Lipid membranes made this way were the first step towards cellular life. Compartments that could concentrate molecules, protect chemistry, enable evolution. On Titan, they form spontaneously, naturally. Not water-based life, something else. Life using liquid methane, the way Earth life uses water. July 2028, less than 3 years from now, NASA will launch Dragonfly, a nuclear-powered rotorcraft the size of a car with 8 rotors capable of flying in Titan's thick atmosphere. It will arrive in 2034 after a 6-year cruise. And for over 3 years, it will hop across Titan's surface like a dragonfly hunting over a pond, sampling dunes, analyzing lake beds, exploring impact craters where liquid water might have briefly existed after asteroid strikes melted the ice. Dragonfly will land near Selk Crater, 90 kilometers wide, formed by an asteroid impact that generated so much heat it melted Titan's icy crust, creating a temporary lake of liquid water mixed with organic molecules. For thousands of years after impact, that crater might have held conditions similar to early Earth. Water, organics, energy, all in one place. Then it froze, preserved. A snapshot of prebiotic chemistry locked in time. Scientists call it a long-running chemical experiment, one that might show us how life begins. Not how it began on Earth, how it begins. The universal steps, the chemistry that's possible anywhere. Titan isn't just an analog for early Earth. It's a laboratory for an entirely different kind of biology. A place where the rules are familiar, but the chemistry is alien. If life can start in liquid methane at -290 degrees, where can't it start? Europa gets the missions, Enceladus gets the headlines. But Jupiter's largest moon, Ganymede, hides the largest ocean in the solar system. Ganymede is bigger than the planet Mercury. It's the largest moon in the entire solar system. And beneath its heavily cratered surface lies an ocean that makes Europa's look modest. Not just one ocean, possibly multiple layers. Scientists analyzing Galileo and Hubble data realized Ganymede's interior might be structured like a club sandwich. Ice shell, saltwater ocean, high-pressure ice layer, another ocean, another ice layer, rocky core. Multiple oceans at different depths, separated by exotic ice phases that only form under extreme pressure. We know less about Ganymede's ocean than the others because nobody's been there since Galileo. But that changes soon. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in 2023. It's taking the slow route, using gravity assists from Earth and Venus. It will arrive at Jupiter in July 2031, and in December 2034, it will become the first spacecraft to orbit a moon other than our own. It will spend 9 months orbiting Ganymede, mapping its ice, measuring its magnetic field, probing its ocean with radar, searching for the same signs we found at Europa and Enceladus, the largest ocean in the solar system, waiting to be explored. Let's step back. Look at what we've found. Europa, global ocean, twice Earth's volume, organic molecules, potential plumes venting directly into space. Enceladus, active geysers, all 6 essential elements for life. Hydrothermal vents, thermal stability for billions of years. Titan. Methane lakes. Prebiotic chemistry. Potential for exotic biology completely unlike anything on Earth. Ganymede. Largest ocean in the solar system. Layered structure. Magnetic field. Waiting. And there are more. Callisto. Jupiter's second largest moon. Probably has an ocean. Mimas. Saturn's cratered Death Star moon. Scientists discovered in 2024 it has a subsurface ocean that formed just 5 to 15 million years ago. Recently. Geologically, yesterday. Dione. Maybe even Miranda, orbiting Uranus. And Pluto. Billions of miles from the sun, cold and dark. Might have a liquid ocean beneath its heart-shaped glacier. The outer solar system is wet, soaked. Ocean worlds are the rule, not the exception. For 50 years, we looked at Mars. We found ice, hints of ancient rivers, evidence it was once wet, 3 billion years ago. Meanwhile, the moons of Jupiter and Saturn were hiding oceans. Not ancient, not dry, not dead. Active, warm, full of chemistry today. We asked the wrong question. Not is there water on Mars, but where aren't there oceans? And the answer shocked us. Oceans are everywhere. We just had to look beyond the Goldilocks zone. We thought you needed a star's warmth, the perfect distance, not too hot, not too cold, to keep water liquid on a surface. Turns out, you don't need a surface ocean. You don't need to be in the habitable zone. You just need tidal heating, radioactive decay, internal friction. Moons orbiting giant planets, squeezed by gravity, warmed from within. The outer solar system is cold on the surface, but beneath the ice, it's thriving. Right now, this moment, as you watch this, Europa Clipper is traveling through space at 39,000 miles per hour. Fast enough to cross the United States in 6 minutes. It passed Mars on March 1st, 2025, stealing a bit of the red planet's momentum like a gravitational slingshot. In December 2026, it will swing past Earth one more time, picking up even more speed. And then it heads outward, into the dark, toward Jupiter. April 11th, 2030. Arrival day, 5 years from now. For 4 years, it will orbit Jupiter, enduring radiation that would kill a human in hours. It will dive past Europa 49 times, each pass skimming as close as 16 miles above the ice, mapping the surface, measuring ice thickness, analyzing chemistry, searching for plumes, looking for the conditions that make life possible. If Europa Clipper flies through a plume, if it samples ocean water erupting from beneath the ice, if it detects organic molecules in patterns that suggest biological processes, everything changes. We're not looking for life directly, we're looking for habitability, the ingredients, the environment, the possibility. But if we find those things, the question becomes unavoidable. July 2028, Dragonfly launches. 6 years of cruising, then 2034, Titan. For 3 years it will explore, flying between sites, sampling chemistry, searching not for life, but for the steps that come before life, the prebiotic reactions that might be universal, the recipe that, given enough time, becomes something more. And beyond that, scientists are already planning missions to Enceladus, an orbiter and lander proposed for launch in the 2050s. It would fly through the plumes dozens of times, Maybe even land near the tiger stripes, drill into the ice, sample the ocean directly. 30 years from now, we might have an answer. Are we alone? For 50 years, we searched Mars for water. We found traces, ancient riverbeds, polar ice, evidence of a wet past, 3 billion years dead. We built rovers to scratch at the surface, orbiters to map the streaks we thought were springs, landers to dig for buried moisture, and we found hints, just hints. Meanwhile, Jupiter's moons were hiding oceans. Saturn's moons were spraying water into space. Titan was raining methane onto alien seas. We were looking at the wrong worlds. 1976. We landed on Mars searching for life, found none. 2005. We discovered Enceladus was venting an ocean into space. Took us 29 years to notice. The water worlds were there all along. We just didn't know where to look. The universe is full of oceans. We just didn't expect them to be hidden. The paradigm was simple. You need surface water. You need a star's warmth. You need to be in the Goldilocks zone. Turns out, none of that matters. You don't need a surface ocean. You don't need to be in the habitable zone. You just need tidal heating, radioactive decay, internal friction, moons orbiting giant planets, squeezed by gravity, warmed from within. We thought Earth was special, a fragile blue marble in the perfect zone where temperatures allow liquid water. But Earth isn't rare because it has water. It's rare because the water is on the surface, where we can see it. April 2030, 5 years from now. Europa Clipper arrives. We'll measure the ice, sample the chemistry, search for plumes venting ocean water directly into space. We'll know if life could exist there. Not if it does. Not yet. But if it could. And if Europa has the chemistry, Enceladus almost certainly does too. Phosphorus, organics, hydrothermal vents, everything life needs. Titan will answer a different question. Can life start without water? Can chemistry become biology, using methane instead? By 2035, 3 missions will be exploring ocean worlds at once. Mapping, sampling, analyzing, searching for the conditions that make life possible. The water worlds weren't where we expected, but they're there, hidden beneath ice, warmed by forces we barely understand, full of chemistry we're only beginning to explore. For half a century, we looked at Mars and saw the past. Now we're going to Europa, Enceladus, and Titan. And we're looking at the future. The search for life didn't end when Mars turned out to be dry. It's just beginning. This is Cosmic Canvas, where we map the oceans we never expected to find. Until next time, keep looking beyond the obvious. The universe hides its wonders in the strangest places.